everyone, and welcome to SPMinar, the Society of Props Managers webinar series for live theater prop professionals. I'm Karen Robbie Vance, SPAM member and actually current SPAM president and the head of props in Minneapolis, Minnesota. The Society of Props Managers, affectionately known as SPAM, was formed in 1994 by a small group of prop professionals in the Midwest to address issues of common importance and to create parity with other production departments. Today, we're an association of 160 plus professional prop managers and educators from non-for-profit producing organizations, opera companies, and educational institutions. We've built an international communication and support network that shares resources, information, solutions, and techniques, as well as safety information, continuing education, and stock. As with previous SPMinars, we're requesting pay what you can donations to help support this programming and our annual grants for early career prop professionals. The window of which for applying for the first round ended yesterday. So I hope some of you applied or know people who did. So if you can afford to donate, links to those will be in the chat as soon as I finish talking here. We truly appreciate any help that you can give us for that. We've enabled live transcriptions for this webinar. If you'd like to use them, click on the show captions button on the bottom of your Zoom window, or you can click the view full transcript to see it in the meeting side panel. I'm joined tonight by my friend Eric Hart, who's a SPAM member and author and the interim director of animatronics at the University of North Carolina School of the Arts. Eric has, in addition to having the prop agenda and 3 incredible books, he's built props and effects for shows on and off Broadway at regional theaters, operas. He's worked on films and commercials. He's been a member of SPAM since 2009. And tonight he's going to be giving us an introduction to animatronics and how we can incorporate them into our own creations. And with that, Eric, I turn it over to you.
Hi, thank you, Karen. And thank you, SPAM, for having me tonight. And welcome, everybody. Like Karen said, I am the interim director of animatronics at UNCSA in North Carolina. So I am actually in the animatronics shop tonight, and I have a lot of cool things to sort of show you. So I figure, why don't I just start off with a little slideshow so that we could kind of talk about what animatronics is. And I'm going to go through that pretty quickly because I do want to get to how you can incorporate animatronics into your props, whether you actually want to build full characters, or if you just want to use the same technology for making animated props. Treasure chests that magically open, rats that run across the stage, papers that shoot out of a malfunctioning printer, what have you. So yeah, animatronics, where objects come to life. I think the first, looking at what we're going to go over, I have the definition, a history, where animatronics are used, what they could do. Then I'll get into how do animatronics work. And finally, how can you make animatronics and use your animatronic technology for animated props. So what are animatronics? I'm sure we've all heard the term before. Most of us probably have some idea of what we think animatronics are. Maybe you've gone to a Chuck E. Cheese restaurant and watched the band play, or you've gone to Disney World and seen Pirates of the Caribbean, or you've played various video games where animatronics come to life and try to end you. Animatronics are used in film, in TV, theater, theme parks, of course. But just breaking down what they are, right? Animatronics, according to Wikipedia, are mechatronic puppets. So they're using some terms that might not be familiar. Mechatronics is basically the study of anything with electrically moving parts. So your box fan is mechatronic. The turntable in your microwave is mechatronic. If you had or have a VCR, either personally or in your prop stock, all of those mechanisms that kind of make it play and eject, those are all mechatronic. So it's items that are functional, right? Animatronics are meant to look like they're alive. They're meant to tell a story. They're meant to have an emotional connection So they're not necessarily functional, but they do share a lot of the technology of mechatronics. So this little Venn diagram, you could see how I kind of think about it. Robotics are a small part of mechatronics. Animatronics overlaps with mechatronics and a little bit with robotics. You could have robotic animatronics. You also have a lot from the world of puppetry. And so you can have mechanized puppets, or you can have kind of remote controlled puppets that are animatronics. And then you have automata, which I'll talk a little bit about, kind of the predecessor to animatronics. These, if you've ever seen the little, you turn a little crank and that makes it move, like maybe it's a cat trying to catch a mouse, a little wooden cat and a wooden mouse, delightful little things, or the fancy clockwork automata from ages ago, like German cuckoo clocks where the woodcutters come out. These are all kind of driven by a single axis. So they're like animatronics, but animatronics are a little more complex because they can change what they do and they could inhabit a much richer world, but still from the same tradition. Again, your robots and your mechatronics, they are trying to complete a task. So this robot on the left, it's moving its arm to pick things up and put them somewhere else. Meanwhile, the animatronic on the right, it's also moving its arm, but it's doing it because it's telling a story. She's trying to find her father. It's not that the arm necessarily has to move from side to side, but it's the motion that best tells the story. So if your technology is not up to the point where you can move her arm, you could probably find some other motion to tell the same story, as opposed to the robot where you need to move the arm to complete the function. So you're doing whatever you can to tell the story. The story comes first with animatronics. The character and the motion are what's important. Actually completing any sort of function is secondary, right? So that's probably the most important thing to keep in mind here. It's the same with props. They have to tell the story. A chair can be a prop. You can actually sit on it, or maybe it breaks away. You can't sit on it, but when you sit on it, it breaks, and that's telling the story, right? You don't want a real chair to do that. So looking at the history of animatronics really quickly, I like to go all the way back to the 1st century with Hero of Alexandria building these wonderfully moving statues that use water or gravity power. Very simple automaton. You know, you open a door and it waves at you, that sort of thing. The Middle East in the 13th century had a wonderful illustrated book of more technologically sophisticated automaton, still using water power to sort of turn all the gears and the cogs. And then again, in 1495, Leonardo da Vinci built this knight that has a lot of pulleys and ropes. I believe he actually just drew it, and it wasn't until later that they built it and saw that it actually would work. But through pulling these ropes and these pulleys, you kind of get this motion. So again, these are simple water-driven, gravity-driven machines that just perform a series of movements when they are turning. We then get into clockwork automaton when you get watchmakers of Europe, clockmakers building these very intricate mechanisms that were spring-driven or gravity-driven with a pendulum. Volkansen in the 1730s had a series of very complicated, wondrous devices. These three, it was a flute player, it was, I believe, a drum player, and then a goose. And the goose could walk around and eat and flap its wings. This was kind of exported over to Japan, and the karakuri puppets from the 17th to the 19th centuries are great examples of very intricate, tiny little characters that would perform all these movements, and they were popular. They were in people's homes, and they would use them during tea ceremonies and other important events. And then we get into the golden age of automaton, where we have these brass characters they had brass innards. Their outsides were often porcelain or maybe paper mache. A lot of them still survive today, and they're still really amazing. I mean, some of the most complex could actually draw pictures. And this was just from series of cams. You just wind it up and it goes. Absolutely amazing mechanisms. We can learn a lot from them. Then with the birth of electricity, this is where we start seeing things that approach our modern idea of what animatronics are. Basically, you could take these complex automaton and stick a motor in it and get even more complicated things. We had these coin-operated fortune tellers that would speak, and they had a phonographic record providing the sound, and their mouth would actually move. So an attempt to sync the figure with audio. And dating from as early as 1889, one of the big carnival automatons was Laughing Sal in the 1930s. These were everywhere. These were kind of mass produced. Some of them still survive today. Wonderful and frightening animation. You know, she would sort of laugh and shake. And scare generations of children. 1940s, Sparko the robot dog, he could actually walk around, driven by electricity. It was built by General Electric as a sort of mascot, but a very important figure in the development of animatronics. Finally, 1961 is when Disney coined the term audio animatronics, and these were figures that would actually be synced with audio. So the Tiki Birds were the first ones that appeared in their theme parks, and they could sing, and the soundtrack would actually cause their mouths to open and close. And so it was a much more complex, programmable figures. And that's kind of the difference with animatronics, is that they're programmable. It's not just whatever you build the crankshaft to do, it's you can change what the figures do depending on the signals that you're sending to them. So a lot of things going on at this time, but really Disney was the one making this technology available to the public with all their figures, Pirates of the Caribbean, It's a Small World, of course. Some of the first ones in film, like Mary Poppins, the little bird, was animatronic. And then we move into the 70s. Chuck E. Cheese was big because, again, bringing animatronics to the public view. These were largely pneumatic figures, but again, highly programmable. They just plop in a floppy disk and they could have a brand new show with the same figures. They'll play different songs on their instruments and sing different words. Their mouths would move, their eyes would move. And they still program them with floppy disks today. The Henson Creature Shop was also big in animatronics. In 1982, they were formed to create the Dark Crystal. And a lot of their innovation was with live manipulation of animatronics. So they wanted to do live puppeteering because they were a puppet company. So they developed electronic controls that allow them to remotely move electronic figures using controls that matched what a puppeteer would be using if they were wearing the puppet. And this actually extended into digital characters. They could do live manipulation of digital characters using the same control. So they won an Academy Award for this system, and it's still used in some cases today. So that's a quick history. And where do we find animatronics today? Again, themed entertainment like theme parks and restaurants, film, TV, and commercials, live performance, retail display. Museums use them a lot. Fashion has been using them quite a bit. There's a lot of toys that are animatronic. And then, you know, surprisingly, but not surprisingly, once you think about it, medical training and clinics use animatronics. It's great for having patients that could simulate various symptoms, you know, a step up from the sort of Annie, the CPR dummy. You could have actual responsive characters. Military simulations too, the same thing. You can have characters that interact with people and they have to respond to them. And of course, children's, pizza restaurant, casinos. So they're everywhere. If anything, you know, despite its long history, animatronics is very much a growing field, and we're seeing more and more places where they could be used. Live theater is very much, I feel it's very untapped. There's not really big companies that are providing animatronics. It's still very spread out, but if you've seen the pictures of King Kong, this is a massive, massive innovation in terms of live animatronics on stage. But just looking at the list here, you can see plenty of shows on Broadway and some classic shows too that use various animatronic elements. Lots of places you can use it in theater. So how do animatronics work, right? That's what we really want to know. That's what we're here for. There's this great sort of infographic I came across years ago. Garner Holt is one of the big California-based theme park animatronics makers, and they're very much a factory of animatronics, and you can see how they break it down with all the different departments. You know, they have they create drawings, they have a metal shop, they're repairing their old ones, they're assembling the parts, they're making the skins and the flesh and the fur and the hair, they're doing molding and casting, they're doing fabric work because the human characters wear clothes. And then they're programming all of these within their shop and testing them to make sure that they're ready to go. So really cool infographic. So if you think about what are the parts of an animatronic character, a lot of people like to think of it in terms of the skin, the frame, and the control. So a character will have what you see, which is the skin, and then what's holding it together, the frame, and the control, which is how you actually move it. And you think of these in separate ways because you want to keep them separate while you're working on it, right? You have the skin of this tiki bird that I have sitting next to me, and the frame, and the skin goes over top, as you can see, right? And again, it's a small world figures. Looking at the sort of drawings, you can see the frame, and then some pictures of it too. The frame holds the mechanical components, and then it has this sort of outer shell, and the skin kind of peels off of it, and you can remove it and put it on, hopefully as many times as you need, right? And that way you can do repairs and paints and all that sort of stuff. I don't know if anybody could recognize that character, but it's very complex animatronic at the time, E.T. the extraterrestrial, showing off its frame. This is the structure that holds all of the components. So you mount the motors to it, you give the axles, the bearings, and the bushings, and you have places to attach the skin. So this is usually, we're building this out of metal or plastic because we want something as rigid and lightweight as possible. Really big animatronics will be welded steel. Smaller, lighter ones, maybe aluminum that's bolted together. And a lot of times you'll find 3D printed ones using plastic frame parts as much as possible, because again, you want it to be lightweight, but still rigid. It needs to produce movement that is as smooth and consistent and reliable as possible. And in some cases, you could use wood, though in definitely the themed entertainment, you get away from that just because it's a bit too heavy. The skin, again, is the visible portion. It could be flesh, it could be fur, it could be clothes or fabric or rigid pieces as well. Fiberglass, 3D printed plastic, all that. It's giving you the shape and the form. Because your animatronic has moving joints, the skin often needs to be flexible and stretchy, right? If you're thinking about an animal, if you built it out of rigid pieces, it would look like a robot. You need it to be covered in a flexible skin that looks like it has muscles underneath it, and that looks like it's stretching and bending and twisting. So it could be really tricky. But the idea of the skin, besides making it look like a character, is also to mask all the mechanical components. while still having sort of secret access panels to allow you to get in to fix anything that you're working on, right? Finally, control is how you manipulate it, whether it's live control or some kind of pre-programmed show that it goes through, or as we're getting into nowadays, interactive control where it can actually react to live things happening, but still not need a live puppeteer manipulating it. There are some very clever solutions for controlling animatronics in the past. Nowadays, of course, you can do everything digitally with dirt cheap components. And so that's how most animatronics are controlled. So maybe you're basing it off of a timer, or you're syncing it to a signal such as audio or video. Or again, you could have live control, which is often what we want in the theater, as well as in film and TV and commercials. Again, this little diagram I drew, you'll program it in some kind of programming environment like your computer or a big console, kind of like a light board. And that will write a program that is then sent to a hardware interface, which controls your servos, your motors, your solenoids, your pneumatic valves, your power. You know, because ideally you don't want your animatronic to be hooked up to a computer at all times. You want it to have some kind of chip or microcontroller living inside of it, so it's kind of autonomous off by itself. So it's important, again, keeping the frame, the skin, and the controls separate. I have some reasons up here. It's basically, it allows these parts to be built separately. You want your metal shop to be working on the frame while your painters and your clothing people are working on the skin, and you don't want shards of metal getting in the wet paint, and you don't want to have to wait for the skin to be done before you could be adding motors. So building it in these pieces, different pieces, and having it sort of come together at the end is kind of the ideal situation. So yeah, we're doing good on time, and now we're up to how can you actually make animatronics? Short of coming here to UNCSA and getting a grad degree in animatronics, maybe you just want to do it at home, right? So looking at a typical process for an animatronic, oftentimes you start with the character itself, the creature itself. You start with the sculpt. Remember looking back at how robots have to complete functions and animatronics have to tell characters. Oftentimes with robots, you're building it from the inside out. You're starting with, what motor do I need? What frame do I need to get sort of the function that you need? Whereas with an animatronic, you build the character first. You're like, I need a baby Yoda. He needs to be this big. Now I have to cram all the mechanisms inside of that. I can't make it any bigger. So you start with the character, and that's usually with a sculpt to have a fully three-dimensional, full-scale character in a kind of neutral pose, right? Once you have the sculpt, whether it's digital or in clay, you can then sort of figure out what kind of shell it lives on. And then you could start figuring out what kind of mechanics go on the inside. And I'll go through all of these in turn, but this is basically an overview of the process. The frame is what holds it all together and supports it. And then the skin is what goes over the shell to make it look like the sculpt again. Figure finishing is a term that encompasses all the finishing to the skin. Painting, adding hair, adding fur, making clothes, additional sculpting, all that sort of stuff, all the stuff that's visible to the audience. Finally, there's assembly where you put your skin and your frame and your mechanics and your shell all together. And then finally, you could test it, right? See if it actually works, see what you have to go back and fix. At the end of testing, you have a fully functional figure, and now you could go in and you could program it. Now you could start making it move the way that you want to move. Maybe it's animating a sequence that gets played over and over again, or maybe it's programming it so that somebody can control it live from off stage or somewhere else on set Lots of different things you could do to program it. So that's your typical process. And you know, maybe you want to go through all of that by yourself and build yourself a personal animatronic, or maybe in a shop, you're breaking that down into different departments and different people kind of building all of that. So starting off, usually your very first thing on your way to a sculpt is some kind of concept art. This is going to guide your process. This is a drawing from Mark Davis for the original Pirates of the Caribbean. He was great at capturing the movement in a two-dimensional drawing. Right away, you could kind of see how this is going to move, right? You could kind of go like, oh, he's kind of losing his balance up there. He's kind of leaning and balancing, and he's probably tipping back and forth, and maybe he's waving his gun around. It's great if you could get a concept art that sort of showcases the potential movement of the figure. That's just going to make every step easier from then on out. A character turnaround is just looking at what this character would look like in 3 dimensions. They used to hand draw every angle of it, like this picture of Goofy from the 30s. If you're drawing and sculpting your character digitally, it's a lot easier to make a character turnaround. You just, you know, rotate the view of your digital sculpting program. But you want to sort of establish, you want to take your concept from 2 dimensions and bring it into 3 dimensions, because ultimately animatronic characters are 3-dimensional, right? You want to, at some point, build a model or a maquette. The maquette's just the French word for model. Usually maquette refers to a scale model, something that's a little smaller, or you could do a digital model where it's full scale. Once you have your maquette, again, you can use that to reference for a full scale sculpt in clay or foam or whatever you want to work in. Or if you want to do it digitally, you can sculpt a scale maquette in clay and then scan it, and then you have a digital model. So there's lots of ways you could do it. You could kind of bounce back and forth between the practical world and the digital world, depending on what you like to do, right? You can still do everything practically, and there's a lot of companies that do. Or you could work on a fully digital pipeline, which is very tricky, but again, some companies do that. Or again, bounce back and forth, whatever you like to do. There's another bit of paperwork animatronics artists use called a function sheet. And this is where you're telling everybody on the team how the character moves, right? So this is a kind of old school function sheet. This rock and roll lion, you can see he's got a body tilt, a body lean, and a body turn. And then looking at the head, there's a head nod, a head tilt, and a head turn. So we would say this has 6 functions, right? So whoever your mechanic is, they're going to have to take look at the full scale sculpt and see what kind of frame and mechanics they need to build in order to pull off all these different moves. And you know, when you make your shell out of your sculpt, you have to figure out how you're going to cut it apart so that the different parts can actually move. And that's where you're going to determine like what needs to be stretchy, what needs to be rigid, all that sort of stuff. You really do. It's vital that you kind of plan this out before you start building stuff, because you don't want to be halfway through and go like, oh, I suddenly want the head to turn, but it's impossible because I didn't plan on that ahead of time. So the function sheet is going to guide everybody on your team, or even just yourself, in terms of what this character is doing. And it's going to show what kind of moves are actually possible with the character, right? The tiki bird that you saw next to me at the beginning, and which I'll show more of, the function sheet had 4 basic moves: the mouth open, the head nod, the head turn, and the neck move forward and back. And then there were some optional ones: wings forward, wings out, maybe the eyes blink with a video, maybe the body has a 4-sway or a side sway. So I'll show you what functions I actually ended up putting into it at the moment. But again, this sort of guided the construction of the frame and the mechanics, and it's a vital piece of communication paperwork to establish early on. Once you have your function sheet and your sculpt, you could kind of start figuring out how to do the mechanics. Maybe you want to mark all the pivot locations where it's actually going to pivot. Here's a character model sheet of this woman, this pizza restaurant employee, and all the different places that her body pivots. Studying anatomy is really good for this step. If you're doing like a human character, the elbow pivots in a very specific location. The wrist pivots in a specific location. But even if it's a fantasy character, there's still going to be some basis in reality in terms of anatomy. So you still want to study it so you kind of know like what's the logical and most aesthetically pleasing place for it to pivot. Once you're there, you could start mapping out how you do the mechanics, right? Again, you're working from the outside in, so you always have to know the ultimate size of your outer shell and skin and make sure everything fits within it, right? It's going to be hollow on the inside. How much room do you have to work with? So having a full scale section cutaway of the skin or the shell is vital, right? If you've done your theatrical drafting, you know how to do section views. So generally, if you have a symmetrical character, you'll kind of take a section view of the very center of the figure and try to fit it all within those confines. Obviously, if like looking at this, it's a bird, you know a bird is round, so the farther out you get to the sides, the less room you have. So you don't want to be assuming you're going to have that full width for the whole depth of the body, right? If that makes sense. Again, generating this full scale drawing and kind of mapping out where you're going to put the mechanics is really helpful. Here, this is a wing, and it has the kind of extents drawn on that paper, and then full scale drawings of all the mechs. And then that was pretty easily cut out of brass plate. I believe this was just cut on the bandsaw, sanded down, filed down with hand tools and drilled. So some pretty intricate animatronics work being done with just the bandsaw and some files and a drill press. It doesn't take like super fancy machine shop technology to do a lot of this stuff. You want to be precise, but you don't need like a plasma cutter or a CNC water jet or any of that kind of stuff. You could do it with a lot of the tools you already have in your prop shop. You can also do all your mechanisms digitally. Again, if you have a digital sculpt, you could kind of shrink down how much room you have on the inside, sort of cut away space on the inside to make it hollow, and then draw everything in 3 dimensions on a 3-dimensional CAD program. And then you know whether it fits or not, right? Before you even build anything. And those parts can then be exported to be cut out on a CNC or 3D printed, or just, again, print it out full scale, trace it onto some brass plate, some aluminum plate, and cut it out with a bandsaw. Even if you model it digitally, that doesn't mean you need digital fabrication tools, right? You can bounce back and forth. Most of the mechs are use what we call linkages. These are a series of rigid bodies connected by fixed or floating joints. So you can see you have a motor on the left, and it's spinning around. And through this series of linkages, it's generating straight motion, right? So you're working with these linkages to figure out the motion you could get from your motors and your servo motors. I like to start out with a skeletal view, so I'm not dealing with specific parts. I'm just establishing how far away each pivot is, how long each rod needs to be, where I need attachment points, all that sort of stuff. It is super helpful to build it with cardboard or craft sticks using brads. Again, the one on the right, it's kind of mimicking what a servo would do. And with just a few popsicle sticks and brads and some cardboard, you can see how you're using a servo to create this back and forth motion. And you can now transfer all of those measurements to metal pieces or to hardware, or to however you're going to build it. So everything's figured out before you're cutting any metal and you're doing anything super complicated. We can all work with cardboard and craft sticks, right? There are also many computer programs to sort of help you out. And you can see here, the two motors are spinning at the same speed. All the rods are the exact same length. We just change where it's connected, but it gives us different movement. So it's really important to kind of model this stuff out and play with it rather than just haphazardly attaching your points, because you want to know what kind of motion you're actually going to get at the end, right? And if you're really fancy, you could get some complicated motion using just linkages. This horse running mech is driven by a single motor, both legs, and you could even build it on the other side and have all four legs driven by a single motor. All of those are just rigid rods connected by pivots, but in the end, they create what looks to be a horse galloping, not trotting, galloping. So you see that a lot in automaton, right? Most motion that we're dealing with animatronics is gonna be either rotary or linear. We're dealing with motors, stepper motors, and servo motors. And for linear, we're dealing with hydraulic cylinders, pneumatic cylinders, and linear actuators. So your regular DC motors, I like them with gearboxes because it makes them go a lot slower. Like this one is, I think, 10 RPM. You don't want something spinning super fast. And then stepper motors, these are the kind you might see on your 3D printers or your CNC machines. These can, they spin very slow, they have high torque, and you can make them start and stop very precisely. So they're really great for rotary motion for animatronics because you need torque. And then kind of the one of the workhorses of these tiny animatronic figures are your servo motors. And these come in all sorts of different styles, sizes. You can put all sorts of different attachments on them. This is some robotic servo motors. And these allow you to get precise positions, right? So rather than spinning, this will move to a specific position and just hold it there. So that's what you do when you're programming a servo, right? You're telling it to move to a specific position. So that's how you get your kind of complicated motion going on. And again, you could see here, this is a simple little treasure box opening and closing with a servo motor mounted in there with a little rod going to it. There's a lot of reasons why you don't want the servo to just be moving the box lid, mostly to do with torque, but also just with assembly and ease of maintenance. So a lot of times you want to think of some connection away from the actual pivot, the actual hinge to make it move. But this is a pretty simple mechanism that anybody can make with just a single servo that costs $15 to $20 and some easy hardware. So the way servos work, you can't just plug them in. You're going to have to use something called pulse width modulation. This is how you position a servo. It's also how stepper motors are controlled, and you can use them to control your DC motors as well. Basically, it's shooting out a series of pulses, and depending on how big those pulses are, that's what position the servo goes to. So, you know, if you've ever hooked up a motor or a light bulb to power, you know, you could just plug it in and it goes. Servos don't do that. You need something controlling the pulse width. But there's some pretty straightforward ways of doing it. There's things called servo testers. There's RC units that allow you to control it live. And then we'll get into the microcontrollers with the Arduinos and all that sort of stuff. So a servo tester, it's basically just a knob You hook it up to the power, and then you hook your servo up to it, and then you test the servo. So this little character has a servo inside of it, and just by turning the knob, I could sweep through all the motion of the servo. So it's meant to test, but honestly, for theater, this might be all you need because you don't have to deal with any microcontrollers or programming or anything. It's just a knob. You just control it. So this was a little violin player my wife and I made for a window a few years ago. Little hand sculpted character. Inside is a 3D printed base and then a servo. And the character's arm is actually mounted directly to the servo arm. I know I just said don't do that, but for something this small, you could do it. So rather than this moving back and forth, it's a human arm with a bow, and it's kind of cute. So you could get servo testers with a bunch of knobs on them for controlling multiple servos at a time. So this is an eye mechanism with the eyes up and down or back and lower lids, a little janky because I dropped it on the way over. But you can see it's got 6 micro servos, each of them controlling this little eye mechanism here. This is, I did not design this. This is something you can find online. You can find lots of them, but this was one. It's all 3D printed parts and then RC airplane hardware that's really easy to buy. And the servos were, I don't know, like $30 for all 6 of them because they're so small. 3D printed parts, again, the hardware, another couple bucks. And then the servo tester, again, you could buy these on Amazon or many other places. Not the most elegant solution, but just to play with it, it's pretty easy and cheap. Again, no programming needed. So yeah, again, like you could find a lot of animatronic modules and parts online. Another thing that a lot of film people use and a lot of theater people use are these RC airplane remote controls. So a little more pricey, but again, you can avoid any sort of programming. All it is it has a series of controls, and then on the other end, you just have a tiny little receiver, and you could plug 6 servos into it, and then you just turn it on and it controls it, right? So now to 4 functions, I could do head up and head down, head turn, and I also got the wings going on this. So both wings can kind of raise up and down. So this is great for your live performance animatronics. You need a character on stage that'll interact with people, or for film, if you're doing some film work. You could have a bunch of these and have multiple operators. It is RC, so you definitely have to check out the frequencies if you're on theater. But again, this is not connected. I'm over here and making it move. So yeah, this is the tiki bird I showed you a couple pictures of. Again, you can see the skin and the frame are separate. These skin pieces, they're just hard shells at the moment. They just bolt right on as needed. Everything could come off so you can access all the frame. And you can see what's going on. Let me power him down so I could actually move it. He's kind of got some servo ear parts. These wings are mounted directly to the servos, but again, the wings are less than a pound, so it's okay. You could put gears on your servos to actually control them that way. That little gear is what's moving his neck up and down. On the inside here, his head is mounted, and you can see this axle is actually being controlled by this servo right here, with again some gears. So this one was all done digitally. So my colleague drew and designed and modeled the tiki bird itself, And then I imported it into my CAD program and used that to sort of build all the mechs. It's a very long process, very tricky way of working, trying to jam a lot of stuff inside of there. So this is like pretty complicated. And I've been printing and assembling and reprinting and reassembling as I put it together and make it work. Because digital is great, but it is just a simulation. And when you put it together, you suddenly realize like, oh, this is actually hitting this, or this is too heavy and it won't actually lift it. But a lot of fun. Once you get into programming, this is where we're talking about like microcontrollers like Arduinos, Pololus, Raspberry Pis. Essentially, these are tiny computers that you tell it could do a pre-programmed sequence like servo, move here at this time, wait 5 seconds, then move to this position. While you're doing that, the other servo move, that sort of thing. You could also build in some interactivity. You could have sensors with feedback. So it's like, hey, servo, if you're stalling out, maybe turn off or something like that. So everything from simple like sequences to more advanced kind of interactive stuff. It can be difficult to just program the Arduino because it ends up looking very mechanical. Real characters, they have very smooth movements. So this is where the final one, the visual show control, this is where you want to work if you really want fluid movement. And this is where it gets expensive. Your Waggle, your Dilder Flute have proprietary hardware to interface with all your servos. But then you also have programs like Botango, which is free. And that's where you can animate a 3D model very smoothly. And once you have the animation how you want it, you can even sync it to audio. It then generates code to send to an Arduino. So you already have your Arduino, you just download Botango, animate your figure, send it to the Arduino, and then that's controlling the servos with this smooth, elegant animation, which is kind of the ultimate goal of what you're doing. So I'll show a few more things. I know we're out of time, but further resources, I'll leave this up for a second. You could go to the YouTube and pause this screen later, but there's a couple online sites, a couple books, and a couple suppliers that are more geared towards animatronics that I find really helpful. And of course, because there's a lot of crossover, studying puppetry and robotics and mechanical engineering and general mechatronics, and any of the kind of maker stuff with Arduinos and servos is also going to be really helpful. So don't think that this is the be all and end all. There are actually very few animatronic specific books out there. And the ones that are out there are starting to age a little bit. So don't think you're going to find like a book on all of this. You kind of have to piece it all together. But yeah, if you don't know Arduino, again, you can plug up to 6 servos into a regular Arduino, or you get a servo shield, they call it, and that allows you to hook up a lot more servos and it will program it. I like these tiny little things. They're called Pololu. Again, you could hook up 12 servos to this. Boom, 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 boom. Put it on your computer through the USB, and there's a little software that comes with it. And you use sliders to position all the servos. So you get it in the position that you want, and then you hit like, take a snapshot, and then you move them to the next position, and you tell it how much time to take to get to that position, hit another snapshot. So it's kind of like stop motion. You're like positioning all of it and making the time in between. And that's how you get like a sequence, a series of motions and that it's moving through. So again, it's very mechanical looking because it's not like you get the kind of robot movement. It's harder to make it sort of like move fluidly, where it's got what do you call it, ease in and ease out and that sort of thing. But very accessible. Again, you buy this, the software is for free, and it's all visual. You're just moving sliders and you're hitting like, take a snapshot. Super easy to figure out and to do. Or again, you know, little servo tester and you're good to go. Just a nod. Make your own figures however you want. Make your puppets. Stick a servo in it. Cool. So I am happy to answer any questions. I know I was talking nonstop, throwing a lot of stuff out there, but again, it's a big field, and I'm trying to jam it all into 1 hour. But let's hear some questions.
It's a lot. That was amazing. I mean, I've been doing crafts for 20 some odd years, and I learned stuff. So a couple questions. Would you recommend lining fabric over moving parts to prevent loose threads from being caught? Like in the first.
Yeah, that's a lot of what the shells are, because you don't want your fabric for sure getting into the moving parts. And that's also where the testing comes in. You want to make sure that like you run it for 120 hours in the professional world, just to make sure that the fabric's not going to eventually work its way into a joint and do that. So a lot of times there might even be like another layer. So you have your shell, and then you might glue like a layer of spandex between the shells, so the actual clothing can't get in to that joint. Yeah. That's
really smart. Shay is curious, and I am too. What's your favorite animatronic you've ever worked on?
You know, just for what it was, these little characters. It was my wife and I, and we did it during the pandemic because our local theater was dark, and we wanted something in the window to have people look at. And so like they were very charming, and it was such a special time for both of us to work on it, and we get to keep all of them. So yeah, they're simple, but a lot of fun.
I remember seeing a picture of that on Facebook, and it was kind of amazing. Caleb notes that the eye mechanism he thinks was designed by Will Cogley on YouTube. I'm curious, going back to Shay's question, what your favorite part of the process is.
Oh, you know, I'm very drawn to the kind of the mechanical part, figuring out how it's going to move and all of that stuff. I love all the other parts, but it's you know, it's one of those things where it's like, what are you thinking about? Like, you know, when you're going to sleep, what are you thinking about? It's like, I'm thinking about, how do I connect all this stuff? How do I build a frame and put some motors on and make it work? And that's, you know, even with my prop work, that's always what I was working on. Like, how does this actually work? How do you make this move? What's the magic that's going on?
I'm with you there. Zoe is curious if University of North Carolina School of the Arts has any animatronics courses available over the summer, and what would be the best way to get started learning animatronics as a beginner?
Yeah, we don't have any classes in the summer, so our program is a graduate school program, and it's a residential program, so you have to be here. As far as getting started, I posted it online, but the Stan Winston School of Character Arts is good with a collection of videos about mostly film animatronics, for sure, but everything from character design and sculpting to the mechanics and the programming and things like that. Once you start looking around, there's a couple YouTube creators who are really good. There's some Facebook groups that are really good, and you find some people who are posting a lot of good stuff like that. And oftentimes I like looking at all those big coffee table making of books for films that feature a lot of animatronics. You could see a lot of like inside and what's going on. But yeah, you find a lot of information here and there. And Garner Holt, which I mentioned earlier, has started an education wing, and they just started they call it Adults Animatronics Camp, and they have a remote version. So it is pricey, but if you have like a group of people, no matter where you are, you can get their kits and have their instructors do synchronous instruction and learn from like a leader in theme park animatronics. If you're in the California area, you could do it there too. So that's Garner Holt.
That's awesome. All right. Alex is curious what the shell is made out of, and I'm guessing it's for your bird there.
Yes. So this is all 3D printed. So the original character was sculpted in ZBrush, and then it was rigged up in Maya for all the moving. At that point, I took that 3D file and I brought it into Fusion 360, and that's where I sort of hollowed it out, made sure nothing's hitting into anything as it moves. And then, yeah, this was all 3D printed on my little Ender 3. All the parts fit on it. They're all small enough so that every part can be printed on it, and it's just regular PLA. So super fast and sleazy just to make sure it works. It's the kind of thing where it's like, once it works, you could get it printed nicer, but when you're prototyping, that's one thing about animatronics. You need to be able to iterate, and test. You can't let any part of the process be so precious that it takes you too long. That's why I said like cardboard and craft sticks. Like you need to build something and then throw it away because it doesn't work. You need to do it over and over again. So yeah.
Cool. With coding with Arduino or Raspberry Pi, do you go from scratch, a template, or do you do AI generated code?
Oof,
or all of the above?
Yes. I have only ever done, look it up online and download it. There's actually like the Arduino comes with a lot of servo stuff that makes it really easy. It's commented out. So you just plop that in as a skeleton and then you add what you need to add. Again, with the Tango. So some of my students are playing with that. I'm not, but that allows you to visually animate a character and then just dump the code out. It's always helpful to understand the code in case there's something going on that isn't quite working. You could go in and sort of fix it. But yeah, I'm kind of like find the bones of it and then go in by scratch and tweak it as needed, just by hand. Yeah.
Here's a question that's kind of a spin on how do you get started as a beginner, but it's what first steps would you recommend for someone looking to break into animatronics from a traditional engineering background, so not coming from the artistic side?
Oh, so yeah, from the when I have engineers coming into the program, it's like you really have to embrace that art side. And so it's really helpful to kind of come up with your own characters, like develop their backstory, do the sketch, and do the sculpt and all that sort of stuff. Because the challenge is taking a character that now exists and is real and building the mechanics on the inside without changing that design, right? So you're not what I see a lot with animatronics with engineers is they'll kind of build the mechanics and then kind of figure out what fits on top of it. You want to work in the reverse, you want to be like, I can't fit a motor in there. How do I still make this character move that way? Oh, if I build this mechanic, the character looks happy and peppy, but I built a sad character. How do I do that? So that kind of like character design, if that makes sense, the sketching and the sculpting and the thinking about like the backstory and all of that, and really embracing that working from the outside in. Have a very definite design that you have to stick with, and then cram everything on the inside there. So that sort of thing. And then, the other thing is you really got to get like hands-on with the materials and learn what different things do by actually touching it, right? Because a lot of times engineers learn the equations and the simulations, and that is great. That's exactly what companies are looking for. But you want to make that leap to where you're breaking out of that and you're seeing what actually happens. Because again, you're going to have to solve a problem when you go from simulation to the real world and it's not quite doing what you want. Then you have to be like, oh, I remember there's a silicone that's a little stretchier and maybe I'll try that. Or, oh, I was looking at how fabric folds in a certain way when you stitch it in a certain way, and that actually solves the problem. Or even just, I have my students just do paper and cardboard automatons, and they have to really explore what paper does as you manipulate it, because again, it's like, oh, this is doing something really interesting. It's not just a back and forth movement. It's got this undulation, even though I'm just doing something that looks like it should be back and forth. So yeah, hands-on materials, embrace the art, the character design. And then again, from the technical side, like pick up a couple servos, get an Arduino or a Pololu or just a servo tester and start playing like with that. Craft sticks and cardboard.
Love to play. Speaking of play, this is from Jody, who's in Wisconsin. As a fan of Automata, have you ever been to the House on the Rock in Wisconsin?
I haven't, no.
You're going to have to come up this way. We're going to have to go. It's incredible.
Definitely.
Nick is curious if the servos you showed with the gears rather than arms come that way, or did you replace the arms with the gears?
Yes, I replaced the arms with the gears. So the great thing, most of the servos have a kind of standard connection. And so they'll come with these like cheap little plastic things. But if you just know what kind it is, it's kind of a toothed connection. Oh, those are. And it's usually either 24 teeth or 25 teeth. And so some of the sites I shared at the end, especially Servo City, they have tons of different connections you could get for it. So here it's just like a tooth connection, but they sell gears that plop right onto the servo. They sell these little discs where some of the holes are threaded, so it's easy to add hardware to it. Again, little metal arms that have some threaded connections. I like these. They're these little shaft couplers. So you put that in on the servo, and then you could just attach a 1/4-inch shaft like directly to an axle with that. So yes, any of those, like there's a lot of robotic systems that have pre-made parts that allow you to kind of, it's almost like a Lego set for robotics, but you could use it for animatronics too. All the parts just kind of like fit together and bolt together. So if you are kind of wary of like metal fabrication, you could just buy like a piece of metal tube or metal plate and the servo mounts to it, and you put a gear on and you get some pulleys and all that sort of stuff. Kind of like a Director set.
The erector sets. Is there a theater prop that made you passionate about animatronics?
I mean, a bunch, but almost 10 years ago, I was doing some puppets for a show called Snow Queen. And this was our Appalachian retelling of Snow Queen. And one in particular was this crow, and it was on the end of a pole and very mechanical. So you're at the end of the pole and you like pull this and the wings flap and you sort of twist this and the head twists and you twist that and the head goes up and down, and a lot of cool little movement. And I built it the one year, and then we were bringing the show back. So I budgeted in to like rebuild it based on what I learned with like lots of nicer materials. So aluminum and like actually like plotting it out and planning it out. So it was a very, it was like just a step away from being an animatronic. They used a lot of those same principles, but it was like, I loved thinking through that, and I loved like having this bird all the way over here that I was controlling over here, but that looked like absolutely lifelike. It was really great. So yeah, I'm always thinking about recreating that as an animatronic one day.
You will. Also, isn't our job cool? Love what we do. And this is the last question from Kimberly, who wants to thank you for your amazing books. They first got into props last year, and the building guidebook has been indispensable. You'll say that also for me. Incredible. They're curious if there are any prop building workshops or seminars you can recommend, or maybe specific YouTube channels, aside from ours, of course, that you favor.
Yeah, I'm trying to think off the top of my head. I found this person through one of the Facebook groups, but his name is Gary Willett. He's been posting YouTube videos for years and years, very traditional. But what's great is because he's been doing it for years, his early ones are like he's machining aluminum, and then his later ones are like he's designing it in CAD and 3D printing it. So he goes through the whole range of technologies. So yes, Gary Willett. I'll throw that up in the Zoom chat.
Awesome.
So that's a YouTube channel. Again, the maker of the iMech has a bunch of sort of tutorials. I want to say it's like Nils Mechanic, if I remember that correctly.
That sounds familiar.
Yeah,
Awesome.
I'm not doing that with a simple Google search. Yeah,
I think the short answer is too, if you're super interested in something, just Google it, just dive in. And as you dive in, you'll learn more and more and more, and you'll find the good spots.
yes. Oh, there's also Khan Academy has I think it's free. It's called Imagineering in a Box. So the Disney Imagineers put this together, and it goes through like step by step how to make your own theme park ride. But a portion of it is your animatronic, and they're put together so well. They'll sort of explain the concepts, and then they'll interview actual Imagineers who built animatronics and how they work, and then they'll give you short little exercises. Like, it's for like middle school kids, but honestly, it's for me, a mid-40s person. I like doing it. And again, it's the same thing. It's having you build movement with cardboard and popsicle sticks, and how are you going to make your animatronic character move? What's their story? That sort of thing. And I think they even have a little software to design your own linkages like right there as well. So you can do it digitally too. So that's a great thing to go through as well.
Yeah, I just posted a link to that in the chat. And Alex Kepler says that wanted to let you know that they teach a high school prop class that will be geeked to know that they attended one of your SPMinars.
Yes.
Yeah. Well, awesome. Thank you so much, Eric. I really appreciate this, and it sounds like everybody else does as well. We're going to wrap this up, and yeah, and say good night. Thank you for a fun, informative evening. We were giving away one of your books of choice, Chendies, and that's going to go to Alex. Is it Pio or Pio? P-I-O? I don't know how to pronounce that. We'll be in touch with you soon, Alex, to coordinate getting that book to you. If you're interested in BAM and are a working prop manager in a nonprofit theater, opera company, or children's theater, or an educator who teaches prop classes, please visit our website or click on the link in the chat that I think I shared a few minutes ago to fill out our membership form. You can find us on Facebook, Instagram, and YouTube. And SPMinar is produced by the Society of Props Managers with special thanks to SPAM members Patrick Drone, Freed, Larry Heyman, Ben Homan, Stacy Horn Harper, Nikki Coulis, Amy Peter, Sarah Pugh, Eric Hart, and myself. Thanks again for watching. Once again, keep your suggestions for future SPMinars coming. We want to know what you want to learn about. The survey is going to hit your inbox shortly, so please fill that out and let us know what you want to hear. Prep on. We'll see you next time. Bye, everyone.